Hi everyone, welcome to another round of IRIS-HEP Fellow Talks. Today we have Storm and Jason. Storm was mentored by Alex. Alex, do you want to say a few words to introduce Storm's work?
Yes, I'm happy to. Hi. So Storm was working together with Oksana and me, and the context of this work was in relation to the so-called Analysis Grand Challenge that we have in IRIS-HEP, where the idea is that we want to demonstrate how to perform an analysis with an evolving ecosystem, which is currently being developed within IRIS-HEP and within related projects. And we want to do this on an analysis facility and also eventually demonstrate that we can do this at scale and provide some new functionality. And we're going step by step towards this Analysis Grand Challenge. And one thing in particular is that's very important here is to ensure that the different tools that we envision to be used actually do work together. And concretely now, what the idea was behind Storm's project is to try this out in practice, to take an analysis, to send it into our pipeline, and to find all the potential issues that might arise, and then consequently to be able to follow up on these issues. And yeah, we'll see a bit in the presentation of Storm about exactly that.
Thanks, Alex. Go ahead, Storm.
All right. I'm Storm. This is my fellowship project presentation on benchmarking prototype analysis codes on the Coffea-Casa analysis facility. Yeah, so as Alex was saying, the motivations for this project are to build towards the IRIS-HEP Analysis Grand Challenge and to investigate these new software tools, analysis tool prototypes that are in development to see what can be tested and improved in order to effectively analyze large volumes of data, such as that from the HL-LHC. This is from the IRIS-HEP website, the pipeline we are looking at for the Analysis Grand Challenge. And this project in particular focuses on 3 of these tools, ServiceX, Coffee, and Cabinetry. And so the specific project objective here is to recreate an Atlas open data analysis, in particular the Higgs to 2Z bosons to 4 leptons channel that was used as one of the channels in the discovery of the Higgs boson. And we want to demonstrate the recreation of this realistic data analysis with Coffee, Cabinetry, and ServiceX, and show how they interact with each other, as well as run benchmarks to compare things like runtime between these methods and with existing methods, and test this on the Coffea-Casa analysis facility. And now I'll briefly go over the tools that are involved in this. First is ServiceX. It's an efficient high-energy physics data delivery service. A good advantage of this system is that you can pre-select specific events and specific columns in the data so that you don't have to transmit the entire data file, and that saves time and memory, and it works well with multiple data formats. The next tool is Coffee, the columnar object framework for effective analysis. This framework has tools for analyzing and plotting event data. And the big advantage of this framework is that it facilitates horizontal scaling on servers and clusters so that we can take full advantage of parallel computing with tools like Dask. And then the last tool we will use is Cabinetry, which is a library for constructing his factory models and bin template fits. And one unique feature of Cabinetry is its declarative instructions used to build models. And it can also have utilities for visualizing the models it builds. And the analysis facility being used for this analysis is the Coffea-Casa facility. It's a prototype facility designed for coffee-based analyses. And like most analysis facilities, it's designed to speed up analysis times and reduce time to insight. And it uses Dask and Jupyter notebooks, and it's built on a Kubernetes cluster. So now to get into the specifics of the analysis that we created with these tools, it starts with Monte Carlo simulation samples and experimental data, and these are found in .root files. And so the analysis needs to process those and then cut down to 4 lepton events, with the sum of lepton charges being 0 and the flavors being 4 E's, 4 mu's, or 2 E's and 2 mu's, as sort of described in the paper where this channel was first analyzed. And we want to compute from the subset of events the invariant mass of the 4 leptons and histogram the distribution of the invariant mass, the 4 lepton invariant mass. As you can see in these output histograms, on the left, we see the original Atlas Open Data plot. And on the right, we can see that we are capable of exactly recreating this output from the original data using Coffee instead of the original implementation, which used just uproot and numpy and awkward array functions. And as far as performance measurements goes, we can see a significant speed up from the original notebook taking 33 seconds to run the analysis with local data and 16 minutes to run the analysis when gathering the data over HTTPS. In contrast, Coffee, both this first Coffee entry using HTTPS to download root files and SurfaceX to run SurfaceX data sources, you can see that it now takes less than a minute to use data from the internet and only a few seconds once you have the data downloaded locally. In Cabinetry, which supports 2 different types of backends, uproot and Coffee-based, are also very fast. Cabinetry is also very fast at running this analysis with local data. And we can see that we saw that also running these codes on Coffea-Casa, we achieved pretty much the same run times as locally. Yeah. And so when working with prototype software tools like these, one of the important things to note when doing a project like this is the difficulties and issues that I encountered when building up these analyses. And so in the next two or three slides, I'll go over some of these things. The first one that I ran into was that Coffee's processor class is very powerful and very useful, but the functions that processor classes need to implement, the input and output data types are sometimes not exactly clear as to what they are and what's going on with those. Another issue that I ran into when working with Cabinetry is that it's not easy to assign different histogram weights to different data files within the same Monte Carlo sample. Cabinetry by default assigns one weight factor to the entire Monte Carlo sample. And there are sort of tricks and ways to make different weights for individual files work, but would rather there be an easy way. And cabinetry, when using the uproot-based backend, supports the built-in functions that uproot has. But when using the Coffea-based backend, it doesn't have these built-in functions, so I had to create my own patch to get it to support built-in functions of the same form. And cabinetry, unlike Coffea, can't readily use HTTPS or ServiceX data sources to get data from the internet during the analysis. It has to have the data downloaded locally into a local file in order to run the analysis with cabinetry. And yeah, so the biggest and most obvious issue that we saw with cabinetry was the cabinetry declaratively specifies histogram variables and cuts to the events. And it specifies these as strings of sort of the event parameters, things like lep-e, and built-in functions, things like square root. But it doesn't support custom functions, so you can't write your own function and pass it to cabinetry. And this results in cabinetry strings being very, very long. You can see this is an actual string that was used in this project to specify 4 lepton invariant mass. And this is very hard to read, and it would be a lot nicer to just pass in a function. Some further difficulties were that running an analysis with ServiceX data sources, it was initially quite confusing. For example, to do multiple data sources of the same general structure with ServiceX, the way it seems to best to do this is to create a dummy data source that doesn't have real data in it. And then from that, build an object stream, and then use that object stream to create the other real data sources. Another difficulty with ServiceX was that it always turns root data sources into .parquet files. And the issue with this is that a lot of the functions I wrote in the Coffea processor assumed that it would be .root data, but I had to rewrite it for .parquet data. And furthermore, Coffea has this function called run uproot job. It's very nice and it's very easy to use, but you can't use it when you have these .parquet files from ServiceX, unlike the original .root files. And a thing we ran into on Coffea-Casa is that because it's on a remote cluster, if you want to use a specific patch or draft feature of a package in your program, you may require some tuning to make that work on Coffea-Casa. So in the end, the outcomes, we successfully ran and studied the performance of these analyses using prototype tools. And I contributed a new example notebook on the usage of Coffea for analysis to the Atlas Open Data Notebook collection. And this project led to the creation of a new milestone task aimed at streamlining the interactions that were explored during this project. And then, yeah, that's all. From here, I have links and references to notably the full code of the project, the analysis grand challenge milestone. And I'd like to also point out that I have a link to PyHap 2021. This workshop, I used a lot of the talks from there to help me build and complete the code for this project. And yeah.
Thank you, Storm. Gordon, you have your hand raised?
Yeah, Storm. Sorry. Yes. Excellent talk. talk and a lot of really good work. I had just one quick question about I think it was your second comment about issues with ServiceX and when it was started with root files, it was producing Parquet files. I was under the impression that the Coffee framework was agnostic. It could load either Parquet or root files. What was it about your processor that was, I guess what I'm asking is, was your processor looking at files or was it looking at the loaded data and having Coffee load the data for it?
Yeah, so I think probably like with a slight change to the way that, so yeah, Coffee does look at the event data inside the file and not the file itself, which means that in general it is data type agnostic like that. But one of the things is that when ServiceX turned this root into a Parquet file, we ended up with the event data was formatted slightly differently than it was for the original root file. And so some of the syntax for accessing a specific variable within an event ended up being different for the Parquet file than for the ones where I built the root file.
Right. Okay, that's super interesting. I was not aware of that difference, and I guess could I follow up with you and I guess Oksana or to find out a little bit more about that, to get a little more of those details.
Sure.
Perfect. Thank you.
Alex, you have your hand raised.
Yeah, I wanted to say thanks a lot, Storm. It was a pleasure to work with you. And I think there's a lot of very tangible outcomes of this, a lot of things we ran into that you nicely summarized here, which we turn into milestones, or we now are concretely working on to try to streamline things a lot. So from the grand challenge perspective, I think this kind of project is extremely useful to try to get everything together and uncover all the things that then we need to iterate on. And the notebooks, everything, all the material is quite useful because this now can form the basis for future iterations, can be used for testing Coffea-Casa. So there's lots of great outcomes here from this. So thanks a lot for all the work.
Any additional questions for Storm? No? Thank you, Storm. Next up, we have Jason.
Hi, so my name is Jason Hipkins. I graduated with a double degree in math and computer science from the University of Maryland, and I'm soon to be a faculty assistant at the University of Maryland. This summer, I had the pleasure of being mentored by Arena, Lucas, and Kyle on advancing an active learning algorithm for excursion set estimation. It's a common problem in science is finding excursion sets of functions. So yeah, we're interested in finding what the shape of the excursion set is. We want to estimate it. And the naive ways of doing this, or the original ways of doing this, are computationally expensive. You can just take a regular grid and try to find what your excursion set would be or your contour would be. But that has a problem with the larger the dimension gets, you have O to the DN runtime, which is very high. And also there's arbitrariness to choosing the grid. So you don't always get actually a good excursion set. You could also try random sampling, but you have no prior information about what you chose beforehand, and you can just sort of spin your wheels and be exploring random space for a long time without learning any useful information about your contour. Why do we care about this? Well, in high energy physics, this is a big deal to study beyond standard model theories and to exclude parameter spaces or do hypothesis testing for different functions or black box functions that we're interested in. You can understand that trying to compute the entire grid for this parameter space can take weeks, it can take days, it's very expensive. So we want to reduce the amount of times we have to call this black box function, or a pipeline usually is what is given to us as a black box function. And we want to know what's an efficient strategy, computationally efficient strategy for finding level sets. We're trying to do that because we want to test hypothesis testing or exclude parameter spaces. We want to discover things about new physics. And the traditional way is very expensive. So the idea to make this a lot faster is active learning. Active learning allows us to explore the parameter space by only finding points near our contour or our threshold of interest. It's balancing the exploitation of our search space and the prior information we have and exploration of our search space. As you can see, there's some points that are farther away because we're just curious as to where is it and how are we going to get there fastest. And we can do that by using a Gaussian process. Generalization of any multivariate normal distribution for stochastic fields is any vector of points from that field can be represented by a normal distribution, and then a finite combination of those stochastic processes can be used to represent a function space, which we can predict what might be the function that our contour set lies on, or what that set actually is. And we do this by constructing a global entropy-based ambiguity measure. Essentially, we want to reduce the uncertainty in our Gaussian process every time we update it, which is defined by a mean in a covariance matrix or a kernel. And by using Bayesian optimization, we can design an objective function and ask the acquisition function, essentially, what's the next best point we want to choose? And what are those points going to improve for our model? So we can solve this integral for our entropy-based ambiguity measure or reduction in entropy a couple ways. We can also add terms to it to solve it in other ways, and we can create different kinds of acquisition functions to explore our parameter space and essentially train our Gaussian process to reach the best estimate of what our excursion set might be. Some pseudocode to just generally describe this algorithm is we're given a black box function. We want to find a p-value. That's our excursion set. We want to find a threshold where t equals 0.05, for instance. And we want to do this with as few queries as possible to our expensive black box function. So we start off with some data set. We can train our Gaussian process with respect to that data set, and then find a predictive mean for our excursion set and the covariance matrix. We evaluate our acquisition function, find the next best point in our parameter space to update our data set with. We then have a new mean and a new covariance matrix, and we've reduced uncertainty in the overall excursion set that we're looking to find. We have a better idea that this is the right excursion set. So far, the work done on this is been 2 packages were created originally by Lucas, and it implements scikit-learn as the backend to model Gaussian processes. And then Arena used gPyTorch to also do the same thing. At first, we were thinking, why do we need both? But there seems to be some machine-dependent differences on these 2 backends based on the processor or the OS that you're using. And sometimes that can affect performance, and so they may be beneficial. Also, there's different features in each backend that you may want to use for particular excursion sets and particular problems you're looking for. And we tried to do this in a very friendly way. I modeled this off of scikit optimization, which is a package that has an ask and tell interface, which basically is a active approach, or optimal design through sequential choices of solving Bayesian optimization problems for finding our excursion sets. You first ask the oracle or your acquisition function, which is cheap to evaluate because you're just numerically approximating this integral here. You ask it, what point do I want? Then you go evaluate that point, you label it, and then you tell the Gaussian process, your model, the new point, you fit it, and now you have a better mean with less uncertainty. What I did with this package is I refactored the 2 backends and created a new package that was able to be extensible to not only scikit-learn, gPyTorch, but also in the future BowTorch, which is a package that is specifically useful for solving Bayesian optimization problems, which is something we're using a lot of in our active learning heuristic. So the way that I solved this was through abstraction. I was able to exploit design patterns in software engineering. There's behavioral, creational, instructional, the three common design patterns. And I used a strategy design pattern to basically break up the way that different classes would be used, because you want to use maybe different acquisition functions. But in order to make sure that I could solve these problems with just one front end, I had to use abstraction and use an abstract factory pattern, where essentially the optimizer or the problem, the Bayesian optimizer class, has no idea what the backend is. It doesn't need to know what the backend is. It's type agnostic. And then because there's so many different options, a proxy was required to be able to communicate between the different strategy choices and the optimizer, which solves your Bayesian optimization problem. I also implemented a warm start, which is where you reuse the hyperparameters from your previous training iteration rather than training all over again. It is a very useful and time savings for training neural nets and other kind of machine learning problems. However, it may need to be tested more because it sometimes can get stuck in a very deep local min, and it won't actually find the excursion sets you're looking for with the least uncertainty possible. So here's just a basic design of the classes I made. So the sampler, the model, and the acquisition function are abstract interfaces, which you can have different strategies to solve them. You have your builders here, which acts as your proxy. And every time you want to create a new optimizer, your builders will take in these abstract interfaces and create whatever it is you want to see. And then the optimizer uses our ask and tell interface. Your problem details stores all the information about your search space, your problem space, result, so you can get diagnostics plotting. And then the learner is actually another wrapper, which extends the API so that we can also do an ask and evaluate, or an evaluate and tell paradigm, which is useful if you already have a function handle for your black box and you don't want to manually query your black box with a new point every time. So there was success in this refactor. There still needs to be more benchmarking done, but we did learn a lot. I was able to increase the speed of the scikit-learn backend by almost 40 times, and the gPyTorch backend even more, which needs to be benchmarked more thoroughly. Some of the issues we discovered was problems with warm starts, and also the package we used for parallel processing to speed up batch acquisition has some issues, again, that are machine dependent and can be different along memory and runtime usage between different machines. The next steps in this project are finishing an abstract design for the factory method for batch acquisition, because we want to use a batch heuristic with any other one of the strategies we pick. We don't want to have that batch heuristic be just stuck with just one acquisition function. We also want to bring back multiple function support, which is handled very differently between scikit-learn and gPyTorch and BowTorch. So that needs some thought out planning. And we need to finish merging the gPyTorch backend. The merge was very big. The entire code base was refactored. So doing small pull requests. And then the end goal here is to Dockerize this whole process and connect this with black box functions or pipelines that are already being implemented for beyond standard model physics theories. And then we can actually hook it up to that with testing, p-values, and everything else. I'd like to show you guys the tutorial. So some of this code still needs to be reworked out in terms of instructions, but it's a very intuitive design. You give it the information about your search space, and you tell it how fine of a grid you want, because we're going from Rn to R, but really it's a computer, so we have to create a finite step size. You create your search space or your excursion problem, and then I use the learner object because it's a little bit easier with the evaluate and tell interface. And all I have to do is just ask for a point. And then if I ask for a point, I evaluate and tell that point. And in the back end here, if I didn't have this evaluate process, you would just say evaluate. and then you would obviously tell it and it would update. Everything is just very intuitive. It's an oracle. The idea is that all you have to do is ask and tell it. And if you don't like the point, you can ask it again. The benefit of this is that this goes much faster. This does not take weeks and days to run. In fact, on my own local machine here, I can run it right in front of us and it'll be finished by the time my presentation is done. So that is the conclusion of my talk. I mean, mostly the results are that this is way faster, and that's never been done before. I mean, we went from weeks and months to just hours and days.
All right. Thank you, Jason. Any questions for Jason? No? All right. Thank you, Jason and Storm. Thank you to the mentors. That's all we have for today.
Thanks, Rob.
Thank you.
And thanks, Jason, and thanks, Storm. That was a pretty impressive work.